on not Zoom, on Blackboard is kind of difficult. So what I'm gonna do is either send, like, if students want the recordings, I'll just send the recordings to their email so they can get it easier.
Okay.
So I'm gonna record this this Zoom session, and you can get this to the to
All right.
get out. And just open back participants in case anyone in the chat. Okay. So it is this. The 2019 exam 2 practice. So this is what we're going to to good questions.
Okay.
So question 1. How many carbon-carbon bonds are there in one molecule of cycloheptane? All right, so cycloheptane, how many carbons make up that ring?
There'd be 7.
Right, 7. So 1, 2, 3, 5, 6, 7. I mean, which carbon? So 2, 6, 7. All right, 7 carbons there. Now, how many carbon-carbon bonds are there in between? So there's 1, 2, 4, 5, 6, 7. 7 carbon-carbon bonds, so the answer is B.
Okay.
Now, 2. What is the correct order of electronegativity of the elements listed? So from the most electronegative first to the least electronegative. You're working with fluorine, nitrogen, oxygen, and carbon. So what's which one of these elements are the most electronegative?
Most electronegative is the F.
Right. Fluorine would be the most electronegative. All right, so fluorine followed by
The oxygen.
correct. So we can eliminate answer choices B and D. So we're seeing A, C. So it's fluorine, yes. Then oxygen. Then what's next?
And then nitrogen.
Right. Nitrogen. Then lastly is carbon. So the answer choice that match that is C.
Isn't it E?
Wait. Yes. It says C. E. Here we
That's
go.
all good. Okay.
All right. So no questions about that question.
Not at all.
All right. Cool. Now, question 3. Which species contains a labeled carbon that is sp2 hybridized? So it says note that non-bonded electrons have not been drawn in. We do know, however, that some of these species would have the electrons. So you would want to draw it in just for clarification. So for example, in 2, there are lone pairs on this carbon, and in 3, there are also lone pairs on this carbon. So we draw them in for clarification. Now, let's look at each of the hybridization of the carbons that are pointed to one by one. Number 1, you have a positively charged carbon. What does that mean?
Wait, could you ask it again? Sorry.
Positively charged carbon on molecule 1. So what does that positive charge mean, that carbon?
It means that it's missing 1 electron.
Is missing electron pairs. Missing electron pairs. So taking that into effect, you have that info. How many electron environments are around this carbon?
There should be 3 of them, so it's
Right.
sp2.
3 electron environments. That means this carbon is in fact sp2 hybridized, because we always have to remember the hydrogens that are not included in the skeletal structure. So just draw a hydrogen in. You're missing lone pairs there, so there's no lone pairs on the C. It's positively charged. 3 electron. So far, 1 is sp2 hybridized. Now, let's look at 2. 2 has this carbon here. How many electron environments?
The carbon it has um it's 3 or 4? Because I don't know if the hydrogen, there's 2 hydrogens.
Yeah, so you count everything, including lone pairs. So you have 2 hydrogens on the carbon, you have a lone pair, and you do have another carbon that carbon is attached to. So that is indeed 4. That is 4 electron environments.
Okay.
But there's something special that can happen with this negatively charged lone pair here. What can happen?
What can happen?
There's something that can happen with this negatively charged electron.
I have no clue. I mean, it's more than carbon's 4, and now there's 5.
So what I'm saying is, you have a lone pair here, right? But if you notice, like the whole molecule, you have it near double bond over, and it's allylic. So whenever you have an allylic lone pair, what can happen between the non-bonding electrons and the double bond can happen?
Like resonance?
Right. Because it's adjacent to that double bond, you can resonate. So the electrons would push a double bond here, make a double bond here, and then the electrons from the pi bond could push out its electrons to this carbon. Now, what type of hybridization do the atoms need to be in order to perform in resonance?
What type of hybridization? You said?
Yeah,
Like sp3?
sp2. Remember, whenever atoms can perform in resonance, whether their electrons resonate or the double bonds they have between them can resonate, they always have to be sp2 hybridized because the electrons is going into that M2p orbital, so you could move it to do the resonance anyways. So because these non-bonded lone pairs can perform in resonance, the hybridization of this carbon here is sp2 hybridized. That is due to the resonance.
So you're saying you have to do resonance here?
Yeah, we're saying that we're looking at the carbon, right? We know there are lone pairs. This lone pair is directly next to a double bond right here. So because of its connectivity near that double bond, it could resonate. And we all know that what atoms that can perform in resonance, they are always sp2 hybridized. So it can change its hybridization due to the fact that it can resonate. So because of that, this carbon, even though it has 4 electron environments around it, it is sp2 hybridized because we can push the electrons from on that carbon into a resonance, changing its hybridization.
Okay. That's interesting.
Yeah, so like once you form the double bond here, right?
Yeah.
After a resonance happens, once you form that, that means that you can really see how it's sp2 hybridized because now you have 3 electron environments, the double bond and the 2 hydrogens.
Okay.
And lastly, let's look at this carbon over here. It does have a lone pair, yes. So how many electron environments are around this carbon?
How many electron environments? You have 1, 2, 3
Mhm.
and 4. Wait, what?
You do. 4-electron environment.
The lone pair counts as 1, or it's like
Yeah.
2?
Lone pairs will always count as 1 because they're a pair. You know,
Oh,
pairs
okay.
stick together. So you count them as 1, and let's not forget the hydrogen. So you have 3 bonds and a non-bonding lone pair. So that's 4-electron environments around this carbon. So that means it's what type of hybridization?
If there's 4 of them, it's sp3.
Right. So sp3 hybridized.
But you're saying there's no
So-
double bonds, so there's no resonance?
No, since there's no double bond in this cyclic structure, there's no resonance at all. So that carbon cannot change its hybridization. It has to be sp3 hybridized.
Okay.
So now it says which species contain an sp2 hybridized carbon? The answer is what? Which answer choice match?
Is D.
Only 1 and 2 have sp2 hybridized carbon.
Okay.
Any more questions on this question?
No, not really.
Let's move on to the next question. I'm actually going to skip question 4 because I want to ask Ben about something with one of these molecules, just so you know I'm not wrong. Right? So we'll skip question 4 for now
Okay.
and go to question 5. So rank the labeled carbon-carbon bonds in order of decreasing bond strength. So you have a triple bond here. One's pointing to a triple, two's pointing to a sigma, or a single, say sigma. 3 is pointing to a double, and 4 is also pointing to another sigma. So which one of these bonds do you know for a fact is the strongest?
What's the strongest?
Mhm.
Probably 1 because it's a
Yeah.
triple one.
Yeah, triple bonds are definitely the strongest bonds. So 1 would be the strongest, so we can eliminate answer choices B, C, and E because it has other bonds other than 1.
Are they they're the longest bond?
Which one's the longest bond?
Like triple bonds, are they known to be longer than?
No, they're
a single
shorter.
bond? Okay.
So
Alright.
because of their shortness, because of how short they are, that's why they're the strongest. Longer bonds would have weaker strength.
All
So we
right.
said that 1 is the strongest. All right, cool. After 1, what do you think comes next?
It's the double bond, so it's
Right,
3.
3 would come next because it's a double bond. Now you're between 2 and 4, 2 sigma bonds. But what do you think we have to pay attention to now to figure out which of these sigma bonds is the strongest?
The hybridization.
Right, hybridization. Because remember, an sp3 hybridized atom, orbital, is weaker than sp2, which is weaker than sp. So we have to look at the hybridization to determine which one of these sigma bonds is stronger. So let's look at the carbons on 2. These 2 carbons are what type of hybridization?
Those 2 carbons are sp3.
Right. They all have 4, the both of them has 4 electron environments around it. So sp3 for this one, sp3 for this one. All right, cool. Now, let's look at the carbons that make up the sigma bond for 4. You have this carbon here and this one. I marked them with different colors because we do see different connectivity between these 2 carbons. So the purple carbon here, what type of hybridization will it
The purple one you meant? Purple one is sp2.
3 electron environments around the double bonds and the two sigma. So that's, wait, you said 3 or 2?
I said sp2.
Oh, right, 2. Sorry, I just want to make sure my ears are kind of playing stupid today.
That's all good. That's all good.
And now the green carbon. What kind of hybridization is this one?
It's sp3.
Right. 4 electron environments around it, so sp3. Now, between 4 and 2, the both sigma bonds, which one do you think is the strongest?
The one that doesn't have sp3, so 4 is strong.
Right.
Wait, yeah, 4 is
You're
stronger.
right. 4 is stronger because we do have an sp2 hybridized carbon orbital that does overlap with an sp3 to make up that sigma bond. So because we do have an sp2 orbital, it is strengthening that sigma bond even more. So 4 is stronger, and then the weakest, I said longest, meant weakest. The weakest bond here is 2.
Okay.
So the answer choice that match is A.
All right. And then you said sp is stronger than sp2?
Yeah, sp
Okay.
is stronger than sp2, and sp2 is stronger than sp3.
Okay. That makes sense. All right.
Let's move on. Question 6. How many pi bonds are there in total in these 3 molecules? So we're counting the total amount of pi bonds we see within the 3 of these. So in the first molecule here, how many pi bonds are there?
You see 2.
Right, 2. 1 each from the double bonds. You see the carbon, oxygen, and from the carbon, carbon. So 2 pi bonds. What about this second molecule here? How many pi bonds are there?
You see 2.
Right. Triple bonds always have 2 pi bonds, always. And now, in the third molecule, how many pi bonds are there?
There's gonna be 1.
Right, only 1 from this carbon, oxygen double. So 1 pi bond. So together, what's the total number of pi bonds you see for all 3 of these molecules?
You're gonna have 5 pi bonds, which is E.
Right. 5.
All right.
So 7. Which of the following molecules have been labeled with the correct net dipole arrow? So remember, the head of the arrow should always be towards what?
The more electronegative one, like the tip of it, yeah.
The more electronegative atoms. And the tail should always be from the least electron.
Less.
So now let's look at each of the answer choices. Does A seem correct? You have the tail coming from top here, going down.
What was that, carbon to carbon? So no,
Yeah.
not really.
Right, no. That arrow should be the other way around because the more electronegative atoms are towards the top of the molecule. So it's supposed to be this way. So A is wrong. What about B? Does that seem correct? The arrow is going this way.
You go from carbon to bromine.
Mm-hmm.
Is it not? Yeah, I'm pretty sure. Bromine's some more, it's under fluorine.
It is under fluorine, but remember, electronegativity increases which way from up and down the periodic table?
Oh, it goes up on the periodic
Right.
table?
Electronegativity increases this way from bottom to top. So chlorine is more electronegative than bromine because it's further up the periodic table. The arrow is supposed to lean more towards chlorine.
Oh,
So,
I didn't notice that.
yeah, B is wrong. What about C? has the arrow going from the nitrogen to the carbon. Is that correct?
No, that is not.
Definitely not. It's supposed to be the other way around, from the carbon going to the nitrogen. So not B, C is definitely incorrect. What about D? It's going from the carbon and leaning more towards fluorine. Is this correct?
Yeah.
Yeah, definitely. Fluorine is above bromine, further above bromine on the periodic table, so it is more electronegative than bromine. So D is the only one with the correct net dipole arrow.
Wait, so just make sure for B, right? You're saying bromine's less electronegative than carbon?
Yeah, because remember you have F, Cl, Er, and then iodine. As you go down the periodic table, electronegativity decreases. So that means as you go up, the electronegativity increases. So that means chlorine would be way more electronegative than bromine. That's why the dipole arrow should lean more towards chlorine than bromine.
Okay. Oh, yeah.
Mm-hmm.
All right, that makes sense.
So now this question. 8. What would you expect to be the order of decreasing first ionization energy for the following 4 related structures? So all non-bonded electrons and formal charges are included, and there's a hint. So first ionization energy refers to the energy required to remove the highest energy electron from a structure.
Required to remove the highest energy?
So the energy required to remove the highest energy from the structure. So we're going in order of decreasing. So we're going from highest to lowest. So one thing you have to remember is that electrons in bonds are always lower in energy than non-bonding electron pairs, right? So that means they're more stable. It is going to take more energy to break the bonds than it is to take away the non-bonding electrons. So first, we have to pay attention to 1 and 2. Now, what's the difference between 1 and 2?
One is missing an electron, while 2 isn't.
So then, what should we focus on to determine the strength to remove electron? These molecules, what?
You mean like the lone, not the lone pair, just like the missing electron on 1, maybe?
Right, it's missing electron on 1. So the difference between 1 and 2 here is their hybridization. That's what we need to pay attention to determine their ionization energy. So 1 is what? What's the hybridization of this carbon?
sp2.
Right. sp2, and 2 is?
Oh, 2? Oh, sp3.
S3. sp2 hybridized molecules are lower in energy than sp3. So that means the sp2 one is more stable. So since it's more stable, do you think we'll need a higher ionization energy or lower to take away electrons from this molecule?
Wait, could you ask it one more time?
Yeah, so 1 is sp2, 2 is sp3.
Yep.
sp2 is more stable and lower in energy than an sp3 hybridized orbital. So what kind of energy would it take to take away electrons from the sp2 carbon here? A higher or a lower?
It was more stable. I mean, a higher?
Right. It's more stable. The hybridization is lower in energy, which means it's more stable. So in those cases, it will always take a high amount of energy to break their bonds or take away electrons from that bond. So 1 would be the highest. I can eliminate answer choices B and D.
Okay.
So since 1 is the highest, sp3, weaker CH bonds, so it will take a less amount of energy to take away electrons from this sp3 hybridized carbon. So 2 comes after 1. Now we're looking at the non-bonding pairs over here. 3, you have a sp3 hybridized carbon, and
Yep.
4 is sp2. But now, what do you think we have to pay more attention to in this case?
4. Wait. Whoa.
The energy of the non-bonding lone pairs. That's what we have to pay attention to for 3 and 4.
Okay.
Because we do have lone pairs on those carbons.
Yeah.
So 3 is negatively charged, while 4 has no charge at all. It's kind of neutral. So that means what about their energy?
What does it mean? You said SP2 is more stable than SP3.
And the non-bonding lone pair here is lower in energy. So it's lower in energy than the sp3. This is higher energy. So between these two, which one do you think would take a higher ionization energy to take away the electron?
The one that's originally lower, so it's SP2.
So it's going to be 4. And then the lowest would be 3, because these non-bonding lone pair electrons, they're already very high in energy. So it's pretty unstable. It's not going to take a lot of energy to take electrons away from an unstable molecule.
Okay. And then you said if something's more stable, it means it has less energy.
Yeah, when molecules are more stable, their electron energies is lower. So in order to take away those lower energy electrons, you're going to have to use a high amount of ionization energy to do that, because it's already stable. It's like, why you want to break us and we're already stable? You're going to have to work for that.
Okay. And then you said just to make sure SP is more stable than SP2, and it's more stable. Okay, so SP is
Right.
more stable.
SP
Okay.
more than sp2, more than sp2.
All right.
So the
Okay.
answer choice that best match is C.
Oh wait, one more thing, right? How do you know 2 was the second most, like the second highest?
Oh, because you have no non-bonding lone pairs on this carbon. So all the electrons are in bonds. Electrons that are in bonds are still lower in energy than ones that aren't in bonds, like 3 and 4. That's always the case.
Okay. All right. Yeah. Yeah. All right. I might need to look that over later
Yeah.
just to verify that. Well, okay. That makes sense.
Next question. 9. Consider the following pairs of molecules. Determine whether the pairs are constitutional isomers, stereoisomers, same structure, or different structures with different formulas. So let's look at pair 1. We can obviously see that they would have the same molecular formula, because they look pretty much the same, right? Same kind of constituents, same chair conformation, no more carbons than one another, no less carbons. So they both have the same molecular formula. So now let's pay close attention to the substituents. We number it. This one's 1, 2, 3. We number this one. 1, 2, 3. So the methyl substituents also fall on the same number of carbons, but there is a difference between them. In the molecule on the left, what's different about these substituents here than the ones on the right?
What, axial and equatorial? Maybe something like that.
They are in axial and equatorial positions, but what do you notice about the methyls in the left molecule here versus the methyls on the right? There's a big difference between them.
It's a big difference. Well, one is like a clockwise direction, and the other one's like counterclockwise. Like
You do
the way
see
you
that,
numbered
yeah.
it.
You do see that. But what I'm trying to get you to see is, in the left, one methyl's pointing up while the other one's pointing down, right? So they're opposite from each other. And when they're opposite, that means they're what? In what type of confirmation?
Axial.
No, trans.
Oh, okay.
Both those methyl substituents are facing opposite from each other. One's going up, one's going down. So this molecule has trans substituents. And in 2, though both those methyls are what? Are they going opposite or the same way?
One's going down left, the other one's going down right. But
Right,
if they're
so
going,
they're both facing down.
yes, so it's cis. That's what you're
Right,
trying
they're
to say.
cis.
Okay.
So pair 1 deals with trans and cis. So that means they're what kind of isomers?
There's stracemers.
Yes, stereoisomers.
Oh,
So we can eliminate answer choice A and B. So pair 1, they're definitely stereoisomers. Now let's look at pair 2. Again, same molecular formula, we can definitely see that. They'll be numbered the same way too. So like 2, 3, 1, 2, 3. Now, is there really a big difference between these methyl substituents here?
wait, before I answer your thing, does it matter where you put the 1 and the 3? Or
Oh
could you
no,
switch those two?
we
Okay.
could definitely switch them because the methyls will always be 1, 3 away from each other. So whichever one you start from, you will always get 1 on 1 and 1 on 3 and the other one.
Okay.
Oh, hold on. For some reason, my laptop isn't charging, but it's plugged in. 1 second.
All right.
¿Tú sabes lo peor, loco?
Dang
¿Tú
it.
sabes que yo soy el que da FAO y el que no me pasa la bola? Porque cuando me pasa la bola, yo me loco y hago todo con la jugada, yo la hago bien. Pero me pasa la bola poco porque yo fallo mucho. Pero yo gozo cuando va que voy, mira.
Sounds good. I couldn't like now it looks more now we're gonna yeah.
Hmm.
Hey. Yeah, like
Unbelievable. Oh. Hello? Uh-oh.
Guys are still here?
Yeah, yeah.
No.
Okay, sorry, my laptop, it was dying. And then it just like, as soon as I plugged it up, it like locked on me.
Oh.
Took me the and it stopped my right. I'll go right to still recording. All right, cool. Thanks. Share screen. Okay, you guys can see my screen. All right, here we go. This is very last. All right, so pair one, stereoisomers. Pair two, the carbons are numbered the same way, same molecular formula. Is there any difference between the substituents, however?
Nah, there's one up and one down on the
Right.
left and right one.
In both cases, both substituents are facing opposite way. So they're both trans molecules. So what do you think these two are then? Are they constitution isomers, stereoisomers, the same or different?
It's gonna be C, the same for pair two.
Pair two is the same molecule. If you name the both of these, they're gonna have the same name. So the answer choice that best match is C. Pair one,
Okay.
stereoisomers, pair two, same structure. Any questions?
Nope.
So let's move on to question 10. How many secondary carbons are there in the following molecule? So what does it mean for a carbon to be secondary?
Be in the middle two carbons. Or have two carbon attached to it.
Right. So secondary carbons have a carbon that's directly attached to two more.
Mhm.
That's what it means. So how many secondary carbons do we see in this molecule? Would this be secondary?
No.
No, primary. How about this carbon?
Yeah.
Yeah.
Secondary right here. This one?
No.
Primary. What about this one?
Tertiary, so no.
Right. Same goes for this.
Mhm.
And then the same thing will go for this card. Tertiary. This one's primary. This carbon is what?
Secondary.
Yep. And the one next to it is
Same. Secondary.
secondary here too. What about this carbon?
Yeah, secondary.
This one here is tertiary.
Mhm.
These two, however, are
Secondary.
Secondary.
both secondary. Tertiary, and then these two are primary. So in total, how many secondary carbons do we have?
1, 2, 3, 4, 5, 6.
Right,
Six.
Answer choice A. Cool. Let's go to the next question. It's an IR spectroscopy question.
Ooh.
All right, not so difficult, not so difficult. So, automatically looking at this IR spectrum, which one of these answer choices can we eliminate?
Alcohol. C.
Right, exactly.
I know how
If you
alcohol.
had an alcohol, around this region up here would have been a broad tongue
Mhm.
like that, but we don't have it. So there is no OH. No OH at all. We can cancel that out. What do we see, however, in this iron spectrum? What can be classified?
Uh, I think that's a carbon chain C2H. The first one that we see.
Which one? This?
Uh-huh.
So
A stretch CH. something like
I think that's the CH stretch. I believe so. But there is one thing we can definitely point out. This peak here, it's a sharp sword, right?
that.
So
Mhm.
sharp sword peaks represent what type of bonding? Remember,
Strong bond. Really strong.
a C double bond O.
Wow.
So whenever you see a sword peak around this region here, is always represented by a carbonyl bond, a carbon double bonded to an oxygen. So we know we have that for sure. So we can also eliminate answer choice A. Now we're between B and D. Can we say it's B? Do you think it's A?
Mm, no.
Right. The answer is no. So I know aromatic doesn't typically show up in what they give you because remember we was looking at a chart with like peaks that you can see, you can like start kind of familiar with. But whenever you have an aromatic species, it'll be around like the region up here. And what you will see, I like to call them 3 mountains. So it'll be like 1, 2, 3. That's how it looks. So whenever you see that, then you know you have an aromatic species. But we don't have that in that region at all. So it can't be B. The answer is D because we do have a CO.
Wait, so we had to memorize everything, or they give us
So
something to identify them.
not everything, but what you do have to memorize, you definitely do have to know the OH stretch. You do have to know this carbon double bond oxygen peak sword. So this sharp sword right here that represents that you definitely need to know. What else? There is another thing you need to know. It's called if you have a carboxylic acid, what happens is in the front beginning region here, you have like this weird beard. So it's like this, and then it like comes down like this again, and it goes. So that's a beard. This would have represented a carboxylic acid. So those type of characteristics, I would advise you to memorize because those are what he'll mostly ask you for too, since it's easier to spot.
Okay.
All right. You said the OH is just a big curve.
Yeah, so it's like a huge tongue.
Okay. What's the thing at the left then in the original problem? That's just like
But right here,
no, the one to the left of that.
oh, this? Honestly, I don't know.
Okay.
Sometimes you just have peaks there that you can't really identify. So I don't know what this one is.
All right.
Let me get some water.
So move on to the next question. Skip a question. What is it? Oh, yeah. Whoops. Question 12.
Yeah.
Each of the indicated CH bonds have different bond dissociation energies. So which of them has the smallest bond dissociation energy? Now, depending on what's formed after you break the bonds will help you with determining whether you needed a high amount of energy for it or a low amount of energy. So let's draw the products after all these H bonds are broken. So when you cleave these carbon-hydrogen bonds, what's going to be formed?
What you cleave them?
Yeah, another way for saying when you break them.
Oh,
CH2. Here was H there. And CH3. So in this case, when you break the hydrogen bonds from these carbons, you form radicals. So let's represent the radicals as one electron dot for each. There's a radical here. There's a radical here. There's a radical here. There's one here. And there's one. So these are all the radicals formed after those hydrogen bonds are broken. So now they're asking you, when you break in one of these bonds, which one took the smallest amount of energy? So if it takes the smallest amount of energy to break a certain bond, what kind of product do you think you're forming in terms of stability?
uh, wait. So when we look at stability, what? No, I don't understand.
So sometimes you break bonds to form products, right? In
Mhm.
most cases, when you break a bond, you either form an unstable product or you break a bond and form a stable product. Now, if you're going to break something and become stable anyways in the product, do you think you need a big amount of energy to do that?
No.
No, because you're going to be stable when that bond's broken anyways. The whole point of molecules is they want to be stable the best way they can. In most cases, when you break bonds, you do form a more stable product. So the less amount of dissociation energy to break the bond will form a more stable product. So we have to look at which of these radicals do we know is definitely stable. So let me number them. We have 1, 2, 3, 4, and 5. Which of these radicals do you know is definitely stable?
B, D, C, and E. Wait.
Said D?
Yeah.
Yeah, you're right, D. Why is it D? So that's radical 4 over here. This radical is more stable. Why?
Because it's not near the double ones. Well, it is
Exactly.
near, but
The radical is near that double bond. It's an allylic radical. So what happens is it could resonate. So this double bond can come down here and the radical can push itself up here. And look where it's pushing itself, in a tertiary position, which is definitely stable for a radical. So because this radical is resonance stabilized, it'll take the least amount of dissociation energy to break that CH bond. Answer is D.
Wait, could I ask why is it not B again?
So why is it not B? That's CB, right? So something. So it's not B because you form a secondary radical here. This is CB. Both the E hydrogen here. So you form a secondary radical. It's pretty stable, yes, but or you can resonate the radical. And resonance always leads to lower electron energy. So that's why it's D. Now, suppose this question asks which of these bonds would take a greater amount of dissociation energy to break it. Which one do you think it is?
Isn't it just A?
It would be A because that is a sp2 hybridized carbon that you're breaking the hydrogen bond from. So it's always going to take a more amount of energy to break a bond that is very strong. sp2 hybridized bonds are strong. So the highest would have been A. The least is D. Any more questions? So let's move on. All right, 13. What is the IUPAC name of this chicken?
Yeah, I like the
Chicken because of the picture. It's pretty cool. Okay, so first, what's the number one thing you should always do when naming a molecule?
count the longest chain.
Right, longest carbon chain. So how many carbons would make up this carbon chain?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
10.
Yes, I count wrong. Yeah.
All the carbons in the chain literally will be the longest carbon chain. So 1, 2, ooh, that's huge. So 1, 2, 3, 4, 5, 6, 7, 9, 10. This is the longest carbon chain. So you do have substituents. You have some methyls, some terpentals. So, yeah. So now, what's the second thing we need to do?
Start from the
Mhm.
longest substituent, which are those.
So we number the chain.
Yeah.
So where would we start number from? What would be carbon number?
And the leg on the left.
Right. So we do see a double bond in the structure, right? There's a double bond right here. The double bond will hold higher priority for where you would start numbering the carbons. So carbon number 1 would actually fall right here.
Mm.
And then it's 2, 3, 4, 5, 6, 7, 8, 9, 10. That is how you'll number the carbon.
Okay.
So double bonds, anytime you see double bonds, they will always hold higher priority because you definitely want the beginning starting carbon of that double bond to start at a smaller number. Definitely. So we numbered the carbon, we got its constituents. Now it's time for the naming. And remember, always name in alphabetical order. So with that being said, what groups would we name first?
2 and 3.
2, 3. We have 2 of these terp-butyl groups, so what prefix will you use?
Die.
Right. Di, tert, butyl. All right. What comes next?
The methyls?
Right.
Yeah.
The methyls. What carbons do the methyls fall on?
1, 6. Yeah. Double
Yeah.
6.
1, 6, and 6. Now there's 3 methyls. So what prefix do we use?
Prime metal.
Right.
Cyclo.
Trimethyl. Cyclo. So what's the carbon name for 10 carbons in the chain? Yeah, decane, right?
Mhm.
So in this
Yeah.
case, we do dec. We do have to include in the ending where the double bond begins. So it begins from carbon number 1.
Mhm.
So when you're doing it, instead of saying cyclodecane, you would say cyclodec 1E. That lets you know you have the double bond started at carbon number 1.
Oh, okay.
So this is the name. 2,3 diterbutyl 1,6,6 trimethylcyclodecane, which matches answer choice A.
Okay. Wait, can I ask you, Mr. Akemi, could you go back to 12 and just explain that again? Because I was talking
12?
to someone. Yeah. I get 13 though.
All right, no problem. So 12, we said that the bond that would take the smallest amount of disassociation energy to break would be this CHD. The reason why is because the product is very stabilized. So you form a secondary radical here, but the radical is right next to a double bond, so you can resonate it. And what you will notice is when you resonate that radical in a double bond,
Yeah.
your radical ends up in a tertiary position after resonance, which is even stabilizing the radical even more. And then resonance happen back and forth. So it'll continue to happen. Anytime resonance can occur with these like radicals and non-bonding lone pairs, etc., you're always lowering the electron energy of the molecule, which is what they're trying to do. In chemistry, we're always trying to create the most stable molecule. So the more you can lower the electron energy, the better
Yeah.
the stability. So
But I
that is D.
But I have a question, right? Isn't number 1 like the carbon, the HB? Isn't that like symmetrically like directly opposite of 4? So wouldn't you just do the same logic for that?
So honestly, you can use same logic. You could resonate it here, and then that radical will end up here, also in a tertiary position too. So yeah, you can definitely do that.
But it's a bigger dissociation energy than the one for D.
Honestly, it's quite the same. So for questions like this, I believe he wouldn't take off points if you had choose A too, because it's the same type of stability it would have with that double bond. I would say that both A and D are right.
A and you mean B or you mean A?
Yeah, D. I would honestly say that A and D would both be use a lower disassociation energy because A can also resonate. Like you can choose the double bond for D, or you can resonate it up here for A. So
That's
this
B, by the
radical.
way.
Yeah, that's me.
Oh,
That's B. That's B.
D. My bad.
Yeah, that's all good. It makes sense. It makes sense.
Yeah. So I would say that both those answer choices are definitely
Yeah, I'm just like
since they're in the
picky.
same allylic position with that double bond.
Yeah. Okay.
Yep. All right. So no questions about 13.
No.
Maybe a little tricky. All right. So 14. The most stable conformation of compound X has what? All right. So let's do this. Stable chair conformation. We have these 3 substituents. This one up here is an ethyl. This one down here, this is a Turks butyl. And the one at the bottom, this is a methyl. So, which of these substituents is the biggest one?
Terbutyl.
Right, the tert-butyl group. So, if you want the most stable chair conformation, that tert-butyl has to fall in what type of position in the chair conformation?
Equatorial.
Right, it has to be equatorial. And since it's on a wedge, that means it's going away from us. So it's going to fall on a down equatorial position in the chair model. So in order for it to be down equatorial, what kind of carbon does this tert-butyl need to be on? Up or down?
Up carbon.
Right, it has to be up. Opposites will always lead the substituents to an equatorial, so it needs to be up. Since that carbon's up, the rest will follow through. That means this one's down, this one's up, this one's down, this one's up, and this one's down. All right, so we push the tert-butyl into an equatorial position. Now let's look at the ethyl. It's on a wedge, so that means it's going which way?
Up.
Right, it's going up. So since that's going up, and the carbon that is on is going to go up as well, what type of position will it fall on?
Partial. Wait.
Right, it'll be axial. When the carbon and the substituents are going the same way, they end up on the axial position always. And last, let's look at our methyl. Our methyl is on a wedge. That means it's going up. And it's on a down carbon. So what type of position will it be on?
Equa.
With Tori. So the most stable conformation of compound X has what? Which of these answer choices match what we came up with?
Okay.
Right, A. An
I say
equatorial
okay.
methyl group and an axial ethyl.
I said
Okay.
okay. That's good.
Wait. Wait, my bad. Go on.
No, I was asking what you said.
Oh, no,
Not
that oh, okay, my bad. I thought you were gonna ask some. No, I was wondering, how'd you get the equatorials again? Because I like forgot how to do this completely.
Oh, that's right. So you get the equatorials because you're paying attention to what type of carbon they're on.
Yeah.
So, for example, this method, it's wedge, so that means it's going up. It's coming towards us, so it's going to face upwards, but it's on a down carbon. So because the carbon is going opposite of the substituent, they will always fall in an equatorial position.
Okay. Oh yeah.
So answer choice
That
A.
makes sense.
Notice they didn't ask you about the tert butyl in the answer choices, and that's only because we already know for a fact that in order to get a stable chair conformation, we have to push the biggest group into an equatorial position. And the biggest group here is the tert butyl. So we push that in equatorial, we just follow up with the rest of the carbons, and now we're figuring out, okay, what is the ethyl going to be? What's the methyl going to be?
All right.
Next question. Which of the following molecules is most reactive? So what do you think we have to pay attention to in this question?
It's electronegativity.
Definitely electronegativity. And what else do you think? Because we do notice what else about these molecules.
So double bond.
Right, we notice double bonds. So in some cases, what could probably happen?
Resonate.
So we're going to look at the electronegativity and if resonance occurs for this question. So let's look at each of them. A, is this the most reactive molecule? Do you think A is very reactive?
No.
No. Why isn't it reactive? What do we see?
The double bond.
So we do see
Yeah.
that the negative charge is on a 4 electronegative atom because of that oxygen, and we can resonate. So the resonance can occur like this. One of the non-bonding lone pairs on oxygen could create a carbon-oxygen double bond pair, and then this double bond can move like this. So it is also resonance stabilized. So that's lowering its energy. So A isn't reactive. Get that out. What about B? Think it's reactive?
Yeah.
So even though this double bond cannot perform in resonance because of how far away they are, we have to remember you have non-bonding lone pairs on a very good electronegative atom is not going to be reactive as well. So that oxygen is very electronegative. B wouldn't be very reactive. It's actually quite low in energy.
Mm.
Okay.
Now we have these two nitrogens, C and D. Between these two, which one do you know is definitely the most reactive?
C.
Right, C. Why is C more reactive than D?
Because D that can resonate down there.
D
The
can
double-
resonate. So you can push one of the lone pairs to form a carbon-nitrogen double bond and resonate this double bond down here. So resonance stabilized again, lowering its energy, making it less reactive. So C would be the most reactive.
Mm.
Any questions?
No, not at all.
Fine.
Wait, but C can resonate to the the lone pair? Can
No,
go down?
the only reason it can't resonate is because of how far apart this double bond is.
Mhm.
You have sp3 hybridized carbons stopping the resonance. So whenever that happens, it's isolated. No resonance can occur with this molecule whatsoever. So that electron will not move anywhere off that nitrogen. It will stay right there, making it more reactive because of that negative charge.
Okay.
Question 6. In the following compound, identify the number of hydrogen atoms that occupy equatorial positions. So let's go around each of the carbons. Can we have an equatorial hydrogen?
No.
No, we already have an equatorial method. It'll be an axial hydrogen, so there's none there. What about on this carbon?
Yes.
Yeah, we'll have an up equatorial since that carbon's going down, so it'll look like this. What about this carbon here?
Yeah. Can go down.
Down equatorial. What about this?
Yeah. Let me see. Yeah.
So for this one, it'll be a no.
No.
What happens is we already do see 3 physical bonds, and we see 2 carbons already attached in a sideways position. So the only other way this hydrogen can go is down axial, like that. It won't go down equatorial, because then it would be like along the same line as the carbon attachment there, which we'll call steric.
Okay.
So there are no equatorial hydrogens on this carbon. What about this one back here?
Yeah, that can go up.
Up equatorial. Yeah. Can none here because we already have all 4 bonds for that carbon. What about this one?
Yes. No.
Yeah.
It'll be up equatorial. And this carbon,
Yeah.
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 down equatorial. Lastly,
Up equatorial.
this carbon again, all 4 bonds. So how many hydrogens take up the equatorial position?
1, 2, 3, 4, 5, 6.
Right.
It'll be 6.
Answer is E.
We don't count the meta group, right? The
No.
meta-
No, we don't count those because they're only asking about the hydrogens. So metals don't count.
Okay.
So next question.
Looking from the left. Okay.
So now, which of the following structures correctly represents this Newman projection from the direction specified? So
Actually,
this carbon here would be the first one. The carbon in the back would be the second. So I'll just put that in blue. Second carbon back. Now, you have the first carbon, right? The tip of this pen would be the first carbon. The
Mhm.
back would be the second. Now the eyeball is looking this way, right?
Mhm.
So where do you think the first carbon is going to be? On the left or on the right?
Like the one on front, you say, of the chair
Yeah,
confirmation?
so the
Yeah.
tip is the first carbon, back
Okay.
is the second carbon. The eyeball is here.
Mhm.
So if I turn it sideways to where the eyeball is viewing, where does the first carbon end up?
On the right.
Right,
The front one?
ends up on the right. So the front is here, back here. So the eye is viewing it from this sideways position. So in order to get it sideways, so we can properly, like identify the correct molecule, we turn it to where the eye is looking. First carbon ends up on the right, second carbon ends up on the left. So, second. Any
Oh, wait,
questions
quick.
on
Oh, wait, sorry to cut you off. Quick question, right? For
Mhm.
his exams, are these questions going to be like this? Like you're going to look from the left or to the right? Not like, not forward? Not like how I'm looking at the Newman projection right now.
Oh, so he will ask you for that too. So in some cases, you're
Okay.
given a Newman projection and you're asked to view from the sides. The way he will ask you to view forward is in some I think the next question isn't it? No, not the next one.
A later
So
question, you mean?
yeah, a later question will come up. But
Okay.
he'll say like down let's say C2 and C3 carbon of, let's say 2-methylhexane. What would be the Newman projection? So that is where you would have a first carbon to second carbon point of view straight down. You'll have to draw the Newman projection. So he
Okay.
will ask you the questions in both types of ways, from sideways and from straight down.
Oh, I forgot the
Ah.
name of this. It's a clit, and this will be
Staggered.
stagger. Yeah,
Mhm.
stagger gouge. Because
So first carbon's on the right, second carbon's on the left. Now, which one correctly represents the Newman projection sideways? On the first carbon, we have what?
the carbon front.
You have hydrogen in front of you.
Hydrogen. Yeah.
So yes, you have your hydrogen. You also have a methyl and a bromine. So your first carbon should have a methyl, a hydrogen, and a bromine. Which of these answer choices do not have that on the first carbon?
A and D.
Right. A and D can be eliminated because they have the wrong substituents on the wrong carbon. So we're between B and C. So from the side, we know the methyl is pointing straight up. So the methyl should be on what type of line?
It should be on.
Linear, the one that doesn't do anything.
The solid line, right? It should be
Yeah.
on the solid because it's going straight up.
Oh, yeah.
Right, it's
Yeah.
going straight.
And the ether too.
So let's do it like this. Yeah. Methyl's going straight up. Now, the hydrogen, will it be on a wedge or on a dash?
Wedge.
Right. It'll be on the wedge. Because when
Yeah.
we look at the presentation here, the hydrogen is coming towards the eyeball.
Yep.
So that means the bromine is on what?
The dashes.
Right. It's going away from the eyeball. So bromine should be on the dash.
Yep.
So that's our first carbon. Boom. Now our second carbon. In the second carbon, we have the fluorine, ethyl, and the methyl. The ethyl is going straight down. So what kind of line should it be on?
Solid.
Solid line, straight down like this. Boom. So our fluorine on that second carbon, should it be on a wedge or on a dash?
Wedge.
Right, it's coming towards the eyeball. So let's put that on the wedge. So that means our methyl should be on what?
Dash.
Methyl's going away from the eye, should be on the dash. Now this is the sideways representation of the Newman projection from the left point of view. So which of these answer choices best matches that?
B.
Right. B. Any questions?
No, not at all.
This question is kind
I wonder what he gonna say when he see a play with a pencil to do that question.
of, oh, he won't say nothing. He'll be like, cool, they're using, they're trying to visualize it. That method definitely helped me when I was doing this type of questions, because I used to put the first carbon on the wrong side, and I'm like, wait, no. So that method, I do encourage you guys to use. It helps a lot.
How many hydrogen?
18. How many hydrogen atoms are there in one molecule of tryptophan? So let's see.
A lot of double
Does this carbon have any hydrogen?
Yeah,
Yeah.
as
Yeah.
one.
Has one. So one hydrogen here. What about this one?
Same.
Yeah, one.
One. This one.
One.
This one.
It will have one.
Are there any hydrogens on these carbons here?
There are
No.
not.
Right, no. You already have 4 physical bonds with all carbons besides hydrogens. With tri, you'll violate the octet group. So no hydrogens on those carbons. There are hydrogens on this nitrogen, so you have to count that too.
Yeah, I like to
3
search
on
that.
this other one over here too. Are there any hydrogens on this carbon?
Yeah, one.
Have 1. What about this?
No.
4 bonds, so no. How many are on this carbon?
2.
Two.
Oops. So that's all. Oh, what about this carbon?
1, 2, 3. Yeah, how one.
One.
Yes. We only see 3 physical bonds, so 1 more bond has to go to a hydrogen. So 1 there. Now, in total, how many hydrogens are there on this molecule?
4, 5, 6, 7, 8. 12.
12.
Answer is C. There are 12 hydrogens in tryptophan. Any questions?
No.
Go to the next one. It's another chair question. So, which is the lowest energy conformation of the following molecules? So you have this skeletal structure. Now, one thing I suggest you do first is number the carbons. Number the carbons. So where would we start numbering from?
From the esto.
Which one? The
Yeah.
one near the methyl or the furthest?
The left one.
Near the metal.
Right, the one near. Start from there because that's where your substituents are closest. So 1, 2, 3, 5, 6. So we do have 2 ethyls, same size, yes, but we would push this ethyl here in the equatorial position, since we do come to it first, the first carbon. So it's going up
So we go put
since
down.
it's on a wedge. Right, so you want it up equal. We put it on a down carbon. Okay, just like that. So that means the rest follows it. Up, down, up, down. This is up. So the methyl is on a dash, so that means it's going what? Which way?
Down.
Right, it's going down. And it's on an up carbon. So what position is it going to be on?
Equal.
That's all. And this ethyl up here, it's on a wedge, so that means it's going
Up.
Right.
So
going up,
that's
and it's on an up carbon. So what position will it be on?
8.
An axial.
Okay, so
So the lowest energy chair conformation has an up equatorial ethyl, a down equatorial methyl, and an up axial ethyl. Which of these answer choices best match that?
C.
Right, C. Now, the reason I said number your carbons first before you do that is because let's say we did it the other way, right? Let's say we did it.
Yeah, it would be different.
Yeah,
Honestly.
it
Because
would.
that ethyl will
Let's
be
not even
down.
know. This is up. Let's say we put this in up equatorial, right? So this would have been down.
Mhm.
This is up, down, up, down. We have a whole different chair conformation now.
Now we have two axials and one equatorial. So
Exactly, two axials and one equatorial, which is definitely an unstable chair conformation because you have two big groups facing the same way, which is going to cause a lot of steric hindrance. Versus the way we did it, where we numbered the carbon first, we have two substituents in equatorial position and one in axial, which is very stable, no type of steric hindrance whatsoever. So questions like this, you got to look out for.
Okay. Wait, question, right? About the first ethyl, how do you know it was equatorial?
Oh, because the ethyl is bigger than methyl. So the biggest group you'll always want to force in the equatorial position, and then once you do that, follow up with the rest of the substituents and see what positions they land on.
What do you mean bigger? You mean like it was number one, so as priority, or you mean like ethyl is literally bigger than
No, like
methyl?
ethyl is bigger. It's a two carbon group
Oh
versus
yeah,
methyl, which is just one.
yeah. Okay. All
Yeah,
right.
that's what I'm.
yeah, kind of like name. You start from the bigger carbon too. So T2.
Okay.
Question of today. Let's
So,
move on to 20. So, which of the following cations would be most stable? Ooh, so you're looking at all these molecules. You're like, well, what am I supposed to do? What do you
Mhm.
think you have to do to determine their stability? What can happen with all of these molecules here?
Yeah, do
Resonance.
resonance.
Right,
Yeah.
resonance. Resonance can definitely occur. So now we're going to resonate each of these carbocations, right? And the one that most stable means what about the resonance?
Ooh.
So the most stable carbocations, you think that'll resonate less or more?
Is it more?
Right, more. So the
Okay.
more delocalized, the stable the resonance, the more stable the resonance. So which of these carbocations will resonate more? Let's find out. Let's start with A. The carbocations here. So we can first resonate it with this double bond here because it's closer, right? So that would be the first move. That carbocation would end up here. Can it resonate again?
Yeah, with the other
Yeah,
double.
with this double bond over here since it's closer. So it can resonate here. That carbocation ends up over here. So A can only resonate twice. This double bond would not participate in the
So
resonance.
we're looking for the one that resonates the most.
Right.
Mhm.
The more you can resonate the carbocation, the more stable it'll be because you're lowering the energy a tremendous amount.
Yeah. Why does that not participate?
Because it's too far away. You see the first movement we did, right? The
Yeah.
carbocation ends up here. So it's not close to this double bond at all. It's close to this one. So then it participates again, this double bond stuff over here. can't touch this double bond at all.
Hmm. That can't move to the right or anything like that?
Mm-mm. So remember, that's why Ben shows this example with the allylic carbocation, right? When you're performing in resonance, it's always the 3 carbons that'll perform in that movement. So when this double bond moves here, the carbocation ends up on the farthest 3rd carbon. Always. It's always between 3 carbons you do resonance. So that's why it'll end up over here and not over here.
Okay. That makes sense a little bit.
Yeah. It's these 3 orbitals that'll perform in the and
Yeah.
then since it landed in a position where it's next to this one, these 3 will perform in resonance. So this double bond moves over here, and this carbocation ends on the 3rd carbon, which is this one. So A only resonates twice. Now let's look at B. The first movement we can do, resonate this double bond down here, because it's near that double. So this carbocation will end up here.
Mhm.
Can it resonate again?
Yeah, the double bond.
Double bond right in the middle. So we can move this up, and then that carbocation ends up where?
Down there, in the
Right.
middle.
Right here, 3rd carbon.
Yeah, so this one go to the
Right.
right.
Can resonate again.
So 3
It's
times.
near this double bond. So move that, and it ends up over here. B can resonate 3 times. So let's just look at the other ones just to be sure. So 2, you have a carbocation over there. First movement we can do, conjugate that double bond down here, carbocation up here. Can it resonate again?
Yeah, and the double bond left.
So we can that carbocation up
And that's it.
right.
So,
This double bond is too far,
Yeah.
so it would not participate in resonance.
and this.
And the last one, here, it can resonate
Mm,
one time. After that, can it resonate again?
no.
No. These 2 double bonds are definitely further. So these 2 not participate in resonance as well. So now we looked at how many times the carbocation can resonate. So which of the answer choices would be more stable?
B.
It's gonna be
Right.
B.
Carbocation is more delocalized, so it's lowering its energy even more, which will be more stable. Any questions?
I have a quick question, right? Sorry like, to do this again. For 19, I just want to make sure. Why do you make the first thing like equatorial instead of axial? Is it just like how you're supposed to do it?
Oh. Yeah, it's how you're supposed to do it because we know an ethyl substituent is bigger than a methyl substituent. So the bigger substituent groups, you always want to push in equatorial position so that it's more stable.
Okay. Oh, that's just how it is, like the
Yeah,
universal law. Okay.
yeah, that's always how it is. For the most stable conformation, you want to push in equatorial.
All right. Okay. Thank you.
You're welcome. All right, question 21. Internal rotation around C2C3 bond, carbon 2 carbon 3 bond of 2-methylpentane results in 3 eclipse conformations. How many different energies do the 3 eclipse conformations possess? So this is definitely the question you was asking where it's like, do we ever get a question you have to draw it from the straight down position? This is a question like that. So first, before we jump into the eclipse lunar projections, we want to draw the more stable conformation, the stable Newman conformation of this 2-methyl pentane first. So I'll draw them out. 1, 2, 3, 4, 5. Methyl 2, 1, 2, 5. So we're going to draw a Newman projection, looking straight down, carbon 2 and 3 here. So 2 would be the first carbon, 3 would be the second carbon, right? So let's draw the most stable chair conformation of that first. First carbon, second carbon. So there's a methyl substituent sticking straight up. So to draw that methyl. So then we see another methyl, let's draw that to the side, and then the hydrogen. With me so far?
Mhm.
Yeah, yeah.
All right. Now our second carbon, which is carbon number 3, see this ethyl group, right? So we'll draw that ethyl group down so it will be more stable. So ET stands for ethyl. And you have your 2 hydrogens on that carbon as well. So this is the more stable chair conformation. Not chair, sorry, Newman projection. Staggered anti, because both big groups are facing opposite. Now, want to rotate so we can see our 3 eclipsed Newmans, right?
Mhm.
So what we're going to do is we're going to rotate the big carbon in the back. The front carbon will remain the same. Big one in the back will be rotated. So if we rotate the one in the back so that we get our first eclipse conformation, what would it look like? What's closer to what?
The ethyl will be closer to the metal on top.
Yeah.
So we're going to rotate it like this first, right?
Oh,
What happens is they start getting close. So the hydrogen will be close to that methyl up there. This ethyl will be closer to this hydrogen down here. This. And this hydrogen would be closer to the methyl down here like this. So we did our first little eclipse 120 rotation, right?
Yeah.
So let's do it again. Do another eclipse rotation. Front carbon is still the same. No, not F, sorry, that's hydrogen. So now, let's rotate the back carbon again this way. What's close to what now?
okay. So now the ethyl is close to the metal on top.
Right,
Yeah.
ethyl would be here. And the 2 hydrogens, one would be close to the methyl here. The other one will be close to this hydrogen.
Yeah.
And see that rotation happen. So this was the first eclipse, this is the second. Now for the third, we're going to do the same rotation. So front carbon still the same. Now, what's different now? Where is the ethyl going to go and the 2 hydrogens from the second carbon?
So the ethyl gonna go in on the metal on the left down,
Right, it's going to be closer to this one now.
Yeah.
and
The
then
hydrogen that was here, it's close to this methyl up here, and the hydrogen that was in the position where the ethyl was, it's close to this one down. So here we have our 3 eclipse conformations, right? Now we're going to relate their energies. How many of these eclipse conformations have different energies?
1 and 2, then 2 and 3 are the same.
Exactly. 2 and 3 are exactly the same because the ethyl ends up close to the methyl in both positions. It's just that this one is close to the one up here, and this one is close to the one down here. But we do see the same energies. There's a methyl close to a hydrogen, same in this one, and these 2 hydrogens are together, same in this one. So these two eclipses have the same energy. This eclipse conformation is obviously different because all the bigger groups are further apart. So in total, how many different energies do we have?
Two.
Two. Now let me ask, if he was to say, okay, out of these structures, which one is the lowest energy conformation? Which one of these eclipse conformations is lower in energy?
One.
Right, one. Because all the big groups are as far apart as they can be. They're not close to each other at all. So it's less steric hindrance happening. Versus 2 and 3, the big groups meet. The methyl is next to the ethyl. There's a lot of steric hindrance going.
I need to learn the vocabulary for that.
Huh?
I need to learn the vocabulary for that. Stereo.
Yes, just steric hindrance. That's when the big groups are close to each other.
That is repulsion. Okay. Number 22.
Question was
Mm,
22. Looking down the C2, the carbon-2, carbon-3 bond, which is the lowest energy conformation of 2,3-dimethylbutane. So you have all these energies here. Which of the answer choices can we automatically look?
the lowest B.
Right, because this is what kind of conformation?
Is eclipse.
Right,
Eclipse.
this is eclipse. Eclipse conformations is always higher in energy than the staggered. The rest is staggered. Okay. Staggered. So now we're between A, C, and D. Now, out of all of them, which one do you think is lower in energy?
D.
Right. So when we look at A, C, and D, we do see it's staggered gauge, right? The groups are near each other no matter what rotation you do. But we do see a difference in how the groups are together. In A and C, they're both kind of the same energy because they all have all 4 methyls next to each other.
Yeah.
That's a whole lot of steric hindrance happening. So these two are both highest. Staggered energy conformation. Versus D. We only have 2 methyl groups next to each other. Still some steric hindrance, yes, but not as much as A and C. So that's why this one is lower in energy. Any questions?
So the closer they are to each other, it's like the more energy that there is. Okay.
Right. Because remember, within bonds, there are electrons, and the electrons are negatively charged. Whenever you try and force like charges together, they're going to always try and push away. They'll never attract to one another, ever. So the closer you get those methyls together, the more repulsion you will have. That activity is what we just call steric hindrance.
Mm. Okay.
Question 23. Consider the following homolysis, I hope I'm saying that right, reaction. What is the most endothermic? So, in an endothermic reaction, what's happening?
Something is like entering. That's
Right.
how I remember it.
Heat
So-
energy is being absorbed.
So we're creating bonds.
So we're what?
We're creating bonds.
Look at the products. We're not creating, we're breaking.
Hmm.
So,
I
in an
thought we-
endothermic reaction, the heat energy is being absorbed to break bonds. That's what's happening. Because we see the products, we see the fluorine and the hydrogen, we don't see a bond between them anymore. They're broken.
So exothermic is breaking bonds.
Exothermic, you're creating.
Ah, okay.
So
Okay.
in an endothermic reaction, you absorb the energy to break the bonds. In exothermic, when you create bonds, it's about the amount of energy that is released after the creation, depending on the energies of the atoms that was created in the first place. So that's exothermic. Now, A, B, C, and D. See different atoms in play, right? You have carbon, hydrogen, break it, nitrogen, hydrogen, break it, oxygen, hydrogen, break it, and a fluorine, hydrogen. So, remember the trend as you go across the periodic table, right? What happens to bond strength? So as you go across the periodic table from left to right, bond strength what?
Decreases?
Decreases.
Question mark? I think increases.
It increases
Yeah.
because the more electronegative atom attached to the hydrogen would have a stronger bond because of the
Okay.
electronegativity. So bond strength always increases across the periodic table. So when you're breaking strong bonds, would you need a large amount of energy to do it or a least amount of energy?
Okay, so if we see the periodic table, that way the energy decreases. So I guess least amount of energy?
Bigger.
Bigger?
Remember, every time you try and break strong bonds, you'll need a huge amount of energy to do so. The bond strength is letting you know that, okay, I'm pretty stable in this bond right now. So you're going to need a huge amount of energy to break me apart from my atom partner because I'm stable. My energy is stable with this too, right?
Mhm.
So this question is about finding which of these bonds is strong and which of them is going to need a huge amount of energy to break. So we have a fluorine, oxygen, nitrogen, and carbon. Which ones is the strongest out of all of them?
Lauren?
Boring? Yeah.
Right. Fluorine is more electronegative. So right now, this FH bond is definitely a strong bond. So because it is the strongest bond, you're going to need a huge amount of this heat energy that's being absorbed to break it. So another way to look at it is when you're breaking strong bonds and creating, I guess, how to say, not weak products, but whenever you look at the reactants and you're seeing that you're breaking strong bonds, it'll be an endothermic reaction. Any questions?
No, I think that makes sense.
Okay. In exothermic, when you're creating stable bonds, you release, when you're creating stable bonds, you're releasing a huge amount. Oh, you release it, you release it. Of course, that depends on what atom you use. But yeah. This question wasn't too bad. Any question?
No, no, no.
All right. So Steve was saying, I think we still have time for some questions. 24, I'm gonna skip because I was looking at this and I'm like, what does this symbol even mean? I have never seen this in my life. I have never even seen this type of question in my life. So I was like, oh no, please. I'm like, wow.
You don't think it's on the exam?
I know IR, it's related to IR spectroscopy, but at most, the type of questions Ben always put on the exam for IR is like what we did when we looked at the graph.
Yeah.
And not even a lot. He might have like 2 questions in that. He might only have 1. But this type of question, you rarely see these type of questions on the exam. But
I
what I
mean,
will do is I will talk to Ben about this question since I've never seen it before.
okay.
And when he explained it to me, I'll like reach out to you guys and I can explain that question. But for now, it's like, whoa, what is this?
Yeah.
I don't know what I'm looking at.
All right.
Question 25. Oh, no, stop it. Which of the following best describes the energy diagram for homolytic cleavage of the indicated bonds CHA, CHB, CHC? Okay. So what's the difference between all these carbon hydrogen bonds? What can we say?
Deep bonds, like triple bond, or
Right,
Double.
hybridization. You can.
exactly. The hybridization. The hybridization of these orbitals from which you're breaking the hydrogen bond off of, they're all different.
Mhm.
So for example, this carbon here, what's the hybridization of this one?
SP.
SP, definitely. What about this carbon here?
SP3.
Yeah.
It's sp3. So that means that this one is what?
SP2.
SP2.
sp2. So you're breaking a hydrogen off of an sp hybridized carbon, sp3 hybridized carbon, and an sp2. So what can we say about the energies of these hybridization? From sp3 to sp2 to sp, which way is the energy being lowered?
Lower. You need a lot of energy to break a really good bond, like a strong bond. So A
Right.
would be the bigger one.
Right. So that means its electron energy is lower. So an sp hybridized orbital is lower in energy than an sp2, and an sp2 is lower in energy than an sp3. So
Yeah.
first, let's put them in order of energies in this energy chart. Which of these charts correctly puts them in order? So we said sp2 is lower.
C.
No, sp is lower than sp2, then sp,
C.
sp3. Right, C.
Yeah, see.
The sp3 carbon is I keep saying sp3. I don't know why I keep starting from that. I'm sorry. So the sp is lower in energy than the sp2 here, and sp3. So when we want to break the hydrogen bond off of these hybridized carbons, which one would take the highest amount of energy?
CH. SP.
Right. The sp bond, since it's lower in energy, it's a very strong bond, right? This electron energy is very low.
Yeah.
So anytime it's low and pretty stable where it is, you will always need a big amount of energy to break it. So from here to here, you need a huge amount of energy. You need more energy to break the sp than the sp2, and then more to break the sp2 than the sp3. You see the
Yeah.
energy differences?
Yeah.
So C is the correct answer choice that best describes the energy differences between these bonds.
Okay.
Any questions on that?
No.
No, not really.
All right.
That's a question for someone.
It's a good question. Now let's go to 26. We have, I think this might be the last question. Might be. So 26. Which orbitals are used to make the molecular orbital indicated for the indicated bond, I'm sorry. So they're looking at this sigma bond here. So carbon and carbon sigma, right? That's what we're looking at.
Yeah.
So we have to determine the hybridization of these carbons because that's what each of the multiple choices is asking. What
Okay.
orbitals make up this sigma bond? So
Oh,
what is the hybridization of this blue carbon?
sp3.
sp3.
Right. There are 4 electron environments around. 1, 2, 3, and including the hydrogen that's not being shown. So sp3 hybridized.
Yeah.
What about the red carbon?
Okay.
sp2.
Right. Only 3 electron environments. 1 from the double bond, 1 from the sigma here, the other one from the sigma. So sp2. So which of these answer choices matches the hybridization of the carbon orbitals that's making up that sigma?
It'll be
Hmm.
D.
D. Exactly. 1 sp2 and 1 sp3 orbital. Questions?
No.
Half time 27.
We
The following structure is not accurately represented by one Lewis structure. What does the actual structure look like? So, what are we doing essentially in this molecule?
You're looking for resonance.
Right, you're looking for the resonance. So the resonance hybrids will always be shown by like a series of dotted lines for how they're moving, right? That's how the
Yeah.
actual structure is always shown. So we need to see what type of resonance can occur. So for one, you can definitely take one of the electrons from nitrogen and move it this way first, right?
Mhm.
Form a carbon nitrogen double bond, and what happens to that oxygen double bond there? After the first movement, what's next?
That double one kind of go up, or
So the carbon oxygen double bond breaks and the electrons get pushed onto this oxygen. So this will get a negative charge. That's the first movement of electrons. So the hybrid so far will look like this for this one, right?
Mhm.
We can also do the same the other way and move the other set of electrons the same way. Create a carbon nitrogen double bond, break this carbon oxygen double bond, give it to oxygen, gets a negative charge. So the hybrid can also be shown this way. So this is the resonance that can occur. It'll never touch this double bond over here. This will not play in the resonance. So which of the answer choices can we eliminate?
C, D,
Yeah, definitely C and D,
and A.
A.
because it's showing the hybrid from the double bond here that cannot play a part in it, so that can't be true. The only answer choice that matched is B, because these atoms here are all sp2 hybridized and can form in resonance. It's cool.
Yeah, that's cool.
28. How many curly arrows are needed in total to convert the following resonance hybrids? So what we're gonna do is, when we're determining what type of movement is happening, we always look at the second resonance that occurs, right? This helps us know what type of movement happened in the first one, so we can draw our curly arrow notation.
Okay.
So as we're starting, we're looking at 2. What is formed in 2?
So that double one on
Right.
the carbon in the middle. What
See a
happened?
double bond formed here, and what else?
A lone pair on oxygen.
Right. That oxygen acquired a lone pair to get a negative charge. So on 1, we're going to include the curly arrow notation to get to 2. So the
Mhm.
first movement, what movement first do you think created that double bond?
The lone pair moving down.
Right, the lone pair on carbon inserting itself here. So it can create that carbon-carbon double bond. Now, in order for that oxygen to get the negative charge, what movement happens?
The double bond on the oxygen went up to the oxygen.
Right. Double bond breaks, electrons move up to oxygen so we can get the negative charge. So far we have those arrows. That's how we get to 2. Now, what do we have to do?
We move the double bond that we just did for the lone pair to the left.
Right, so we're trying to understand what happened in 3, right?
Okay, yeah.
So we're going to look at
Yeah.
3, and we're going to say, okay, what kind of movements occurred in 2 to get 3? So you notice that the oxygen doesn't have the negative charge anymore.
Mhm.
Yeah.
The carbon-carbon double bond has moved here, and now the nitrogen has gained the negative charge. So the first movement would come from what do you think?
The double bond on the right.
Nitrogen.
It'll come from the electron on oxygen.
Uh,
So first, this moves down before the double bond, right?
yeah.
Now, you have to break this carbon-carbon bond and move here because you don't want to violate the octet rule. Then, break the double bond on nitrogen and push the electrons onto the nitrogen so you get the negative charge. That's the movement we would do. If you had just moved the double bond first and then break the nitrogen, you will have a negative charge on both the oxygen and the nitrogen, which isn't correct.
Oh, okay.
Okay.
So now, we did all that in 2 to get 3, right? So
Yeah.
now we look at 4. What type of movement occurred for 3 to become 4? So nitrogen no longer has a negative charge, but we do see a negative charge on a carbon down here. So what would the first movement come from?
The lone pair for the nitrogen can come down to make a
Exactly.
double bond.
Right, just like this.
So the double
What's the
bond
next? Mhm.
on bottom. Well, no, the double
Yeah,
bond.
this one here.
on the top. Yeah, I was saying the other one, but no. Move
It'll
to
move.
the middle.
Yeah, right, exactly. Because we do see a double bond formed here. Now we just need to push electrons onto that carbon. So how would that happen?
That double bond go to the carbon. Like
Right.
Yeah, just point it.
The electrons from this double bond breaks, pushes onto carbon, so this has a negative charge. That's how you get to 4.
Okay.
So in this hybrid, this resonance hybrid movement, these are the movements that occur back and forth all the time. So in total, how many curly arrows notations did we have to use to show the movement for all the resonance here?
7.
7D.
Yeah. D. Yeah.
Okay. I forgot to include this.
Oh,
Because that nitrogen got a negative charge. I thought I did that. I know I said it,
yeah,
right?
you
I know
say
I
it.
said
You
it,
say
but
it.
how
you
come
said
I
it, you
didn't
said it.
show? What the heck? I'm sorry. I thought I wrote it the same time I said it. I guess I got distracted. So in total is 1, 2, 3, 4, 5, 6, 7, 8 curly arrow notations to show the resonance. I'm sorry. I really don't know how. I know I said it, but for some reason I ain't drew it. Here. So you guys understand the movements though, right?
I
Yeah.
have a question, right? So picture like in number 2, you see the oxygen on the right side with the purple arrow. When you move a lone pair, right? Do you move the 2 dots or you just move or
So
are
it's
you able
4
to move
o'clock.
1 dot?
And we got to question 28. This concludes our office hours.
Well, you didn't hear.
So if you have any questions, please feel free to email me. Yes. I don't know
Wait,
why
Mr.
I
Kemi.
can't hear you guys.
Bruh.
Oh, she's not hearing us. Okay.
Not
So,
you. You're the one answering most of it.
For some reason, I can't hear.
no, she can't hear me right now. I don't know why.
Yeah, she said also she's recording the session. She's gonna just email her for the recording, by the way. And there was one like last week or
Mhm.
earlier this week, and you should email her for that also.
Oh, I thought she sent it us. Well, I have never looked at it.